In this presentation on relations and functions, we are going to discuss various types of relations. Now let us consider that we have a non-empty set A and there is a relation R defined on this set A. There is a relation R defined on this set A. Then this relation is said to be reflexive if for each A in the set A, that is for each element of the set, that element is related to itself. So this thing we can also write, that is for each A in A, this small a, it is representing the element, capital A is representing the set. We are saying that element A is related to itself. So we give an example to make the things more clear. We are saying let A is equal to the set 1 to 3. We are talking about a relation R1 and it is given in this way. It has elements 1, 1, 2, 2, 3, 3 and 1, 2. Now we are going to check whether this relation is reflexive or not. So we can see over here that if we are talking about the first element we have over here, it is 1. Look at this value over here. We are saying the first element of A, it is 1. And from this relation, it is clear that 1 is related to 1. Similarly, the second element in this set A, it is 2. It is related to itself 2. Then we have this element 3 in the set A. It is related to 3. So we are saying 1 is related to 1, 2 is related to 2 and 3 is related to 3. It means for each element of the set A, that element is related to itself. So what we obtain is that this relation, it is reflexive. Now suppose we consider another relation R2. It is 1, 1, 2, 2, 1, 2 and 2, 1. So if we look at this relation, what we have is the first element of A, we have it is 1. Then we are saying that 1 is related to 1. It is clear over here. 2 is related to 2. But 3 is not related to 3. It means that this relation we have, it is not a reflexive relation. Now the next kind of relation we have, it is symmetric. So we are saying that a relation, we have the set A, there is a relation R defined on it, and we are saying that relation is symmetric if we are talking about two elements A and B from A. And we are saying if A and B are related, then B and A are also related. So we are saying that if A is related to B, implies B is related to A for all A, B belongs to A, then that relation is said to be symmetric relation. Now we consider the examples over here. So we are saying, as we have discussed in the previous case, suppose I am considering this relation R2. So in this case, what we have to check is, we are saying that if A is related to B, then we should have B is related to A. So in this case, we can check this condition. We are saying this is the representation of this relation. So what we have is 1, 2. Look at this element over here. We are saying 1, 2. Look at this element. It means that 1 is related to 2. What this thing means, 1, 2 belongs to R means that 1 is related to 2. Then we should have an element such that 2 is related to 1. And from this condition, it is clear that 2 is related to 1. So in this diagram, we can see this is element 1. We are saying 1 is related to 2. Then 2 is related to 1. And similarly, we have 2 is related to 1. We have the element that 1 is related to 2. So we are saying that this relation R2, it is symmetric relation. We have this relation, it is symmetric relation. Now coming to the relation R1, we have the elements, it is 1, 1, 2, 2, 3, 3 and 1, 2. Now look at this relation over here. We are saying that we have an element, that is, we are talking about this, it is 1 is related to 2. We are saying 1 is related to 2. So in this case what we obtain is, we are saying the value of a we are having it is 1, the value of b we are having it is 2. So what we have is a is related to b, or we are saying a comma b belongs to R, but there is no element b comma a belonging to R1 for this particular case, as we are saying that 2 is not related to 1. So clearly what we obtain is that if we are considering, we are saying that a is equal to 1 and b is equal to 2, then a is related to b does not imply in this case that b is related to a for this particular value of a and b. And the condition that we have is that this relation, this condition, it should hold for all pairs AB. So what we obtain from this is that this relation is not a symmetric relation. The next kind of relation we have, it is transitive relation. So we are saying a relation is transitive if, now we are considering three elements. We are talking about the three elements A, B, C in A, the set A. And we are saying if A is related to B and B is related to C, then this thing implies us that A is related to C. So we can write it in this form, that is, if A is related to B and B is related to C, if this condition is satisfied, then we must have A is related to C. So we look at an example over here. Suppose I am talking about this relation R3. So in this relation, we have, first of all, we are talking about it is 2 is related to 2. Then we don't have any element. We are saying we have condition, we are considering value of A is 2, value of B is 2. Now further 2 is not related to any element. Moving on to next element, we have the element 3 is related to 3. There is no element, we are saying A is equal to 3 and B is equal to 3. Again, we don't have any element, other element over here which satisfies the condition for this reflexivity. Third, we are saying that 1 is related to 2. It means we are saying the value of A we have it is 1 and value of B we have it is 2. Now corresponding to this element, we have another element. We are saying 2 is related to 2. So we are saying B is equal to 2 and C is equal to 2. So we have obtained the elements. We are saying A is equal to 1, B is equal to 2 and C is equal to 2, such that we are saying A is related to B and B is related to C. Then we are saying we have an element. From this we are saying we have an element 1 comma 2 which belongs to R. So this satisfies the condition of transitivity. We are saying that if A is related to B, A is related to B means we are talking about this condition that 1 is related to 2 and B is related to C. We are saying that 2 is related to 2, then this implies us that A is related to C. We are saying that 1 comma 2 belongs to R. So what we obtain from this is that this relation that we have, it is a transitive relation. Now if we look at the diagram over here corresponding to this relation, we have this diagram and we can see over here that this relation we have, it is further neither reflexive nor symmetric. Why? Because look at this number 1 over here, it is not related to 1. We are saying that 1 is not related to 1. It means that this relation is not reflexive. Further, we are saying it is not symmetric because we are saying over here that 1 is related to 2 but 2 is not related to 1. So we are saying that this relation, it is a transitive relation, but it is neither reflexive nor symmetric. Now suppose we are talking about another relation. We are talking about the relation R4. It has these elements. It has 1, 1, 2, 2, 3, 3. These all relation, these are on the set A. It has elements 1, 2, 3. So clearly this relation we are talking about, it is reflexive. Further, we can check that it is symmetric. That symmetric means we have to check for every element. We are saying for 1, 2 belongs to R. This implies 2, 1 belongs to R. We are saying for 2, 1 belongs to R. This implies 1, 2 belongs to R. Then we are talking about the element 2, 3 belongs to R. This implies 3, 2 belongs to R. Similarly, we are saying when 3, 2 belongs to R, this implies us that 2, 3 belongs to R. So what we obtain is that this relation, it is symmetric. Now we are talking about the case transitive, and we are saying that this relation is not, but this relation we are talking over here, it is not transitive relation. This relation is not a transitive relation. Why? Because we can find the elements over here. It is, suppose I am talking about the values, I am considering A is equal to the value 3, B is equal to 2, and C is equal to 1. I am talking about these three numbers. Now what we have is, from this we are saying, what we have is that 3 is related to 2. We are talking about this element. We have 3 is related to 2. Further we have, from this element we are saying 2 is related to 1. We are saying 2 is related to 1. We have A is related to B, B is related to C. But there is no element. We are saying 3 is not related to 1. So what we obtain from this is that this relation, it is not a transitive relation. So the diagram corresponding to this relation, it is given over here. So we are saying, corresponding to this diagram, what we can say that we have this element 3 over here. We are saying 3 is related to 2. We have 2 is related to 1, but 3 is not related to 1. So this is an example of a relation which is reflexive and symmetric but not transitive relation. Now the next definition we have, it is equivalence relations. So we are saying a relation R on a set A is said to be an equivalence relation if it is reflexive, symmetric, and transitive. It satisfies all these three properties. So we look at an example over here. So we are saying let Z be the set of all integers and R be the relation on Z defined by this condition. We are saying A and B are related by this relation R if A minus B is even. So we have to prove that this relation, it is a reflexive relation. So first of all, we are going to talk about reflexivity. So for reflexivity, we are considering an element A in Z. Now corresponding to this element A, we are using the definition of this relation. It is A and B are related if A minus B is even. We have this element A. We have to check whether A is related to A or not. So A is related to A means we are calculating the value of A minus A. A minus A, clearly it is 0. A is an integer, A minus A is 0. And this number, it is an even number. So this implies us that A is related to itself. So we have proved that for all A belongs to Z, we have A is related to itself. So this relation, it is reflexive relation. Next, we have to prove symmetry. So for symmetry, we are considering two elements A and B in Z such that A and B, they are related to each other. Now we are saying if A and B are related to each other, then by the definition of this relation, by the definition of this relation, we have A minus B is even. Now we know that if a number is even, then the negative of that number is also even. Now the next question we have is, let A be the set of all triangles in a plane, and R is the relation defined like it is, we are saying R, it is equal to, we are talking about two triangles, delta 1 and delta 2, they are related to each other if delta 1 is congruent to delta 2. This is symbol for congruence of triangles. Now we have to show that R is an equivalence relation on A. It means we have to prove that this relation, it is reflexive, symmetric and transitive. So first of all, we are going to prove that this relation, it is reflexive. So we are saying if we consider any triangle, the set, the given set we have, it is A be the set of all triangles in a plane. So this set A, we are saying it consists of triangle, and we are considering any arbitrary triangle from this set. And we know that every triangle is congruent to itself. So this implies us that delta comma delta belongs to R for all delta belongs to A, and this proves that this relation R, it is reflexive. Now second thing, we have to prove that it is symmetric. So we are considering two triangles from this set A. We are saying delta 1 and delta 2, we are considering these are the two triangles such that delta 1 is congruent to delta 2. So we write it in this way, that delta 1 comma delta 2 belongs to R, and R is the relation which represents delta 1 is congruent to delta 2. Now we are saying that if two triangles, delta 1, we have two triangles and delta 1 triangle is congruent to delta 2. We are saying delta 1 is congruent to delta 2. So this thing will imply us that delta 2 will also be congruent to delta 1. So we are saying delta 2 is congruent to delta 1. Now look at these two conditions. We are saying delta 1 is related to delta 2 if delta 1 triangle is related to delta 2 triangle. Now we have is delta 2 is congruent to delta 1. So what this thing means? This implies us that delta 2 is related to delta 1 by the relation R. The second triangle is related to the first triangle. So we have proved that if triangle 1 is related to triangle 2, then triangle 2 is related to triangle 1. So this proves that this relation, it is symmetric relation. Now third thing we have to prove is that it is a transitive relation. We have to prove that it is transitive relation. So we are considering three triangles, delta 1, delta 2 and delta 3 from this set of all triangles in the plane. And we are considering that the triangle delta 1 and delta 2, they are congruent. Further, triangle delta 2 and delta 3, they are congruent. Now we are saying if delta 1 is congruent to delta 2 and delta 2 triangle is congruent to delta 3 triangle, then clearly we have is that delta 1 triangle is congruent to delta 3. Now using the definition of this relation, we can see that this implies us that delta 1 triangle, we are talking about this condition, that if delta 1 is congruent to delta 3, it means that these two triangles, delta 1 and delta 3, they are related by the relation R. So what we have proved over here is that if delta 1 triangle is related to delta 2, delta 2 is related to delta 3, then we have proved that delta 1 is related to delta 3. So we are saying that this relation, it is a transitive relation. So we have proved all the three cases, that it is reflexive, symmetric and transitive. It means that this relation R on A is an equivalence relation in A. Now the next question we have is, let A be the set of all lines in a plane and R be a relation on A defined in this way. We are saying that two lines L1 and L2, they are related to each other if L1 is perpendicular to L2. Now we have to check whether this relation is equivalence relation or not. So first of all, we are talking about the reflexivity. So we know that any line, it is not perpendicular to itself. It means that L cannot be related to itself for any line L from this set A. So this implies us that R is not a reflexive relation. Second condition we have, if we check for the symmetry, we have let L1 and L2, they are two elements of A which are related to each other. So L1 is related to L2 means that line L1 is perpendicular to L2. We are saying L1 is related to L2. This means that line L1 is perpendicular to L2. If L1 is perpendicular to L2, this automatically means that L2 is perpendicular to L1. And if L2 is perpendicular to L1, so this means that L2 and L1, they are related by this relation R. It is by the definition of this relation. So what we obtain is that this relation R is a symmetric relation. Now third condition, if we have to check whether this relation is transitive or not, we are saying let L1, L2, L3, these are the three lines we are talking about, and they are such that L1 is perpendicular to L2 and line L2 is perpendicular to L3. We are talking about the condition that we have a line, we are saying this is the line L2 and L1 is perpendicular to this line L1, it is perpendicular to L2, and this line L3 is perpendicular to L2. Then clearly what we have over here is that L1 is not perpendicular to L3. So what we obtain from this is that if L1 is related to L2, that is L1 and L2 are perpendicular, L2 is related to L3, but we do not have over here that L1 is not related to L3. We don't have L1 is related to L3. So what we obtain is that the relation is not transitive. So if in this problem we have to tell whether this relation, if suppose this question may be in two forms. First form is we are saying we have to check whether this is an equivalence relation or not. So if you have to check whether it is an equivalence relation and we obtain that it is not reflexive, so you can directly write from this thing that this relation, it is not an equivalence relation. But if the question asks that you have to check whether it is reflexive, symmetric and transitive, then you have to give the complete proof. Now the next question we have is, let S be the set of all real numbers and R be a relation on S. It is defined like R is equal to A and B, these two elements, they are related by this relation R. If 1 plus AB is greater than 0, we have to prove that this relation is reflexive, it is symmetric but not transitive. Now to prove that this is reflexive, we are considering an element A that is a real number. So A belongs to S and we are going to prove that A is related to itself. So if we are saying that A is related to itself, it means 1 plus A into A should be greater than 0. This thing we have to prove. So we are saying then 1 plus A into A. From where we are getting this term? We are getting this term from this relation. We are saying we are talking about whether A comma A it belongs to R or not. So we are considering the element 1 plus A into A. And this value we have, it is equal to 1 plus A square. And this value, it is always greater than 0 because A is a real number. So A square is always greater than equal to 0. So 1 plus A square is always greater than 0. And this thing implies us that A is related to A by this relation for all real numbers A. And hence we obtain that R is reflexive. Now next we have to prove is that this relation is symmetric. So for any two real numbers A and B, we are considering that A is related to B by this relation. So if A is related to B, it means by the definition of this relation, we have 1 plus AB is greater than 0. Now if 1 plus AB is greater than 0, A and B, these are real numbers. So by commutative law, we have 1 plus BA is greater than 0. This value is also greater than 0. And if 1 plus BA is greater than 0, now compare this value with this given relation. So this implies us that B and A, they are related to each other. So what we obtain is that if A is related to B, then B is related to A. It means that this relation R is symmetric. Now next we have to prove that this relation is not transitive relation. So we are going to give a counter example over here. So what this counter example means, that we are going to give an example that disproves a given statement, proposition, or a theorem. So in this particular case, we are going to give an example which disproves that this relation, it is transitive. So suppose I am considering an element that is minus 1 comma 0. It is belonging to R. Why it is belonging to R? Because if we calculate the value of 1 plus minus 1 into 0, clearly this value is greater than 0. So what we obtain is that minus 1 comma 0 belongs to R. That is minus 1 and 0, they are related by this relation R. Suppose we consider another element, it is 0 comma 2. So if we calculate the value of 1 plus AB corresponding to this element, we are saying we are calculating 1 plus 0 into 2. Clearly this value is again greater than 0. So what we obtain from this is that 0 comma 2, it belongs to R. That is the elements 0 and 2, they are related by this relation R. Now if we consider the element minus 1 comma 2, we have to, if this relation is transitive, then minus 1 and 2, they are related by this relation. But what we obtain is that if we calculate the value of 1 plus minus 1 into 2, clearly this value is not greater than 0. So what we obtain from this is that minus 1 comma 2, it does not belong to R. So this example, it shows that we have obtained some ABC. We are saying that there exists ABC. We are talking about this value. We are saying there exists ABC, where the value of A, we are saying it is minus 1. The value of B, we are saying it is 0. And C, we are saying it is 2. Such that A is related to B, B is related to C, but A is not related to C. So we have obtained the elements A, B, C. So this thing proves that this given relation, it is not a transitive relation. So we are saying this is a counter example corresponding to this condition. Now next question we have is, let S be the set of all real numbers and R be a relation in S, and it is defined like that R is equal to the two elements A and B, they are related if A is less than equal to B. We have to prove that this relation is reflexive, transitive, but not symmetric. So first of all, we are going to talk about symmetry. We are going to check the symmetry. So we are considering an element A belongs to S. It means A is a real number. Then using this relation, we have A is less than equal to B. Then A and B are related. So what we have, we are going to check whether A is related to itself or not. It means we have to check whether A is less than equal to A or not. And for all real numbers, we know that A is less than equal to A. So this implies us that A comma A belongs to R. That is the element, the real number A. It is related to itself by this relation. So what we obtain is that A comma A belongs to R for all A belongs to S. The second thing we have to prove it is the transitivity. So to prove that this relation is transitive, we are considering three elements. We are saying A, B, C, these are three real numbers. such that A and B, they are related by this relation R, and B and C, they are related by relation R. So we are saying that this implies us, but this first condition, A comma B belongs to R, it means A is less than equal to B, because this relation is given to us. A comma B, they are, A and B, they are related if A is less than equal to B. So we are saying A comma B belongs to R implies A is less than equal to B, and B comma C belongs to R implies B is less than equal to C. So from these two results, we are saying A is less than equal to B and B is less than equal to C. We can write that A is less than equal to C. And if A is less than equal to C, we are talking about this value, compare it with the given relation. So this implies us that A comma C, they are related by the relation R. So we are saying that for any arbitrary elements A, B, C, if they are real numbers, then we have proved that if A and B are related and B and C are related, then A and C are always related. Now, the third thing we have to prove over here, that this relation is not a symmetric relation. So to prove that it is not symmetric, we are going to give a counter example. We are going to give an example to show that it is not a symmetric relation. So we are considering two elements. One is the element 4 comma 5 belonging to R. So we are saying why 4 comma 5, we are saying it belongs to R because it is satisfying the condition that 4 is less than equal to 5. And we are saying 5 comma 4, it does not belong to R because 5 is not less than equal to 4. We are saying that if we are talking about the numbers, we are talking about this relation, and what we have, we are considering two numbers 4 and 5, and we have 4 is less than equal to 5. So this thing implies us that 4 is related to 5. But for real numbers, we know that 5 is not less than equal to 4. It means this implies us that 5 is not related to 4. So we have obtained the number A and B, where A we are saying it is 4, B we are saying it is 5, such that A is related to B, but B is not related to A. So we have obtained, we are saying that we have obtained a counter example in this case. So we are saying that this relation that we are talking over here, this relation R, it is not symmetric relation. Now the next question we have is, let S be the set of all real numbers, and the relation on this set of real numbers, it is defined like A and B, they are related if A is less than equal to B square, and we have to prove that this relation is none of reflexive, symmetric and transitive. It means we have to give the counter example in all these three cases. So in the first case, when we are talking about non-reflexivity, we have to give an example of a number which shows that A is not related to itself. So suppose we are saying we are considering a number 1 by 2 which belongs to S. Now if we calculate the value of 1 by 2 square, that value is 1 by 4, and clearly this value is not greater than equal to 1 by 2, or we are saying that 1 by 2 is not less than equal to 1 by 2 square. It means that 1 by 2, it is not related to 1 by 2. So this is a counter example, because when we are saying that the relation is reflexive, we are saying A is related to A for all A belong to the given set. So if we have found an A which is not satisfying this condition, it means that this relation is not reflexive relation. Next, in the second case we have to prove that it is not symmetric. This relation is not symmetric. So in this case, we are considering the numbers, say 1 by 2 and 1. These are the two real numbers we are talking about. So clearly we have 1 by 2, it is less than equal to 1 square. So look at this condition over here. We are saying A is less than equal to B square, then A and B are related. It means what we obtain is, this implies us that 1 by 2 and 1, they are related to each other by this relation. Now, if we look at the condition that 1 is not less than equal to 1 by 2 square, so this implies us that 1 and 1 by 2, they are not related by this relation. So we are saying the condition that we have is, if we consider two elements A and B that belong to S, and A is related to B, then we should have B is related to A. We are saying we have obtained A is equal to 1 by 2 and B is equal to 1, such that 1 by 2 is related to 1, but 1 is not related to 1 by 2, and hence we are saying that this relation is not a symmetric relation. The next case we have is, it is non-transitivity. So for non-transitivity, we are considering three elements. Say I am talking about 2, -2 and 1. So these are the three real numbers we are talking about. Now first case we have is 2 is less than equal to -2 square. So what we obtain is that 2 is related to -2. Second thing we have is -2 is less than equal to 1 square. So what we obtain is, in this case we are saying that -2 is related to 1. But now we are saying if this relation is transitive, we have the condition that A is related to B and B is related to C, then A is related to C. A should be related to C. It means that 2, we have to check whether 2 is related to 1 or not. We have to check this thing. So in this case, we are saying that 2 is not less than equal to 1 square. So what we obtain is that 2 is not related to 1. So this thing proves that the given relation, it is not a transitive relation.